Hello, class. So in this video, we're going to still continue talking on section 5.1. Now we're going to introduce new notation here. As you saw in the first video or first couple of videos in this section, if we're trying to do a Riemann sum to approximate the area under a curve and above the x-axis, as we saw, the more intervals I use, the more accurate the approximation is, right? We saw that in the first example, right? When we're doing an approximation with 2, 4, and 8 subintervals. The one with 8 subintervals was the most accurate, which means in practice, we would want to do Riemann sums with 100 terms, 1,000 terms, 1,000,000 terms, okay? Now, it's not going to be feasible for us to write it as we're doing it, right? We don't want to write, oh, change in x times f of a plus change in x plus times f of a plus change in x plus, we don't want to do this 1,000,000 times. So what we're going to do is introduce notation that simplifies this, writing up this addition. Okay. So what's this notation? I'm just going to go ahead and give you examples. Okay. So here I wrote, this here is a sigma. It's a Greek letter capital sigma. Okay. So this means the sum from k equals 0 to 6 of k. Okay. How do you read this? As I mentioned, the Greek letter is sigma. This is the starting index. This is another color. This number here is called the starting index. And then this number in the top is called the ending index. So how do you read this? What does this mean? What this means is start with k equals 0, and you're going to add everything. Right? So add k as k goes from 0 to 6. Okay. So start with k equals 0 plus k equals 1 plus k equals 2 plus k equals 3 plus k equals 4 plus k equals 5 plus k equals 6. So we add k from k equals 0, the starting point, to k equals 6, the end point. So see, this is a shorthand way to write 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6. Instead of writing that, you can just write the sum from k equals 0 to 6 of k. If we add all of this up, we get 20, I believe. Okay. Now we can get we could do things that are a little bit more complicated. So for example, the next one I did was the sum k equals 1 to 4 of k cubed. What does this mean? Add k cubed as k goes from 1 to 4. So what is this going to be? It's going to be 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. Right, so we go from the starting endpoint, which is, cube, not square. We go from the starting index, which is 1, k equals 1, start cubing until we get to the ending index, which is 4. Now for the last one, again, we can get even a little bit more complicated here. So the last one is the sum k equals -1 to 4 of 2k minus 1. Okay. So if you see here, there's no restriction on the starting index. We can start k wherever we want, and we can end it wherever we want. So just as before, what does this mean? It's a shorthand way to write, well, add 2k minus 1 as k goes from -1 to 4. So we have 2, plug in k equals -1, minus 1, that's the first one, plus, now k equals 0, right, because we're going from k equals -1 to 4. So plus 2 times k equals 0, minus 1, plus, now k equals 1. So we do 2 times k, which is 1, minus 1, plus, now we do k equals 2, right? So 2 times 2 minus 1, plus, now we do k equals 3, 2 times 3 minus 1, and then finally we end at k equals 4, right? Plus 2, oops. So plus 2 times 4 minus 1. So you see, instead of writing this whole thing, I can just write it in this sigma sum notation. Again, this is called sigma sum notation because of the capital Greek letter sigma. So you can call it sigma sum notation. Okay. Now we can go ahead and simplify this. We get 2 times -1, that's -2 minus 1 is -3, plus 2 times 0 minus 1, that's -1. So minus 1. 2 times 1 minus 1 is 1, so plus 1. 2 times 2 is 4 minus 1 is 3. 2 times 3 is 6 minus 1 is 5. And then 2 times 4 is 8 minus 1 is 7. Which ends up being -4 plus 4, those cancel, plus 5 plus 7 is 12. So basically, what's the idea here? Whenever you have a pattern, as if you want to add just numbers, integers cubed, so integers cubed, or an integer times 2 minus 1, whenever you have a pattern like that, you can always write it as a sigma sum. Instead of writing the whole thing out, like we did here, you can just use the sigma sum notation. Okay? So that's the idea. Now, we want to use this for the purposes of calculating Riemann sums. Okay? As I mentioned, the more subintervals you use, the more accurate your approximation is going to be. Okay? So what do we want to do? We want to be able to use this sigma sum notation to instead of writing this whole thing here that I was talking about, we can just write it like this with sigma sum notation. So how is that going to look like? Let's see an example. Okay. So use sigma sum notation to write the summation that will approximate the area under the curve f of x equals x squared plus 1 on the interval -1 to 1 with 50 subintervals. Okay. And they want us to use a left and right sum. Okay. So 50 subintervals. We don't want to write that sum 50 times. So instead, we want to find a pattern. Okay. So the process still starts the same. Always find the change in x. So what's the change in x in this case? You subtract the endpoints, and divide by the number of subintervals. So we get 2 over 50, which is 1 over 25. So each subinterval is going to have length 1 over 25. Okay. Now, we know that we're going to be, let's say we're doing a left endpoint. So let's start with the left endpoint. So let's do a sub l. What is this going to be? So I'm going to start the sum just doing one rectangle at a time, but I'm not going to do all of it because I don't want to do 50 terms. And then we're going to convert it to Riemann sum, to sigma sum. Okay, so let's start. For the first rectangle, the length is changing x, 1 over 25. And then f, we're doing left endpoint, so evaluate it on the left endpoint, which is -1. Okay. For the next one, the length is still the same, but now we want to add 1 over 25 to the left endpoint. So this is -1 plus 1 over 25. For the next one, the length is still the same, 1 over 25. Now the next endpoint is going to be -1 plus 1 over 25 plus 1 over 25. It's the same as 2 over 25. Plus the next one. Now we have -1 plus 2 over 25 plus 1 over 25. So we add the change in x again. That's -1 plus 3 over 25. We do this all the way until where? What's the last one? Well, I told you before that if you're doing a left endpoint, where do you want to end? You want to go up to n minus 1, where n is the number of subintervals. Okay. So here we have n equals 50. So how many times are we adding 1 over 25 to -1? Well, we're adding it 49 times, right? Because we start at -1, then we add 49 times 1 over 25. That adds up to 50 subintervals. So this one's going to be -1 plus 49 over 25, which is the same as adding 1 over 25 49 times. Okay. Now, if we want to reduce this as a Riemann sum, right? So we don't want to write this whole thing. We just want to write it with Riemann sum notation. What do we want to do? Well, we're going to have k starting somewhere, ending somewhere, and we're going to have some expression here. What does this look like? Okay. Well, in each term, we always have 1 over 25. So we can just plug that in there. Now, the only thing that's changing here, right, because here we're always multiplying by f of negative 1 plus something. That something is the only thing that's changing. Okay. How is it changing? Well, for the first term, there's none of them. For the second term, there's 1 over 25. For the third term, there's 2 over 25. So how can we do this? Well, it seems to me that it works if we do k over 25. And we start at k equal at 0, and we end at 49. And we can see that this works, right? Because if we go ahead and rewrite this, what is this going to be? So when k equals 0, we get 1 over 25 times f of negative 1 plus 0 divided by 25, that's negative 1. When k equals 1, we get 1 over 25 times f of negative 1 plus k equals 1 divided by 25, 1 over 25. So you see this matches. We do this a bunch of times until we get to the last one, when k equals 49. So k equals 49 divided by 25. Oops, sorry. Okay. So we can rewrite this whole thing here. Instead of writing it out the long way like I did, we can go ahead and just write it the short way, just using the sigma sum notation. And again, what did we do? We identified that in each term in the sum, there's only really one thing changing. The thing that was changing was this 1 over 25 that we were adding, okay? So when I write this as a sigma sum, okay, the only thing changing in the sigma sum is the k, right? So it makes sense to relate the k to the thing that's changing. So I say, okay, I can write k over 25, and I can start at 0 and go all the way to 49. And you see that it matches. It's the same thing. Now, for more practice, let's do now a right endpoint. Okay. Now, as before, to find the endpoints for the right, you just need to find the first one in the first subinterval and add change in x. Okay. So what's the first subinterval? Remember, we have the interval negative 1 to 1. We're dividing it into 50 subintervals. Well, all I'm interested in is what's the first one. So for the first right endpoint, we have to find what negative 1 plus change in x is. So negative 1 plus 1 over 25. That's the same as negative 25 over 25 plus 1 over 25. Same as negative 24. Oops. It's the same as negative 24 divided by 25. So that's the first sub endpoint. The first endpoint, the first right endpoint of the first subinterval is negative 24 so negative 24 over 25. Okay. So now that we know that, we can go ahead and just calculate the sum. So what's the sum going to be? Well, the change in x is always the same. Remember, the change in x was 1 over 25. Now we go ahead and do this. So length is change in x times f of, well, times the function evaluated at the first right endpoint, which is negative 24 over 25. And as I mentioned, once you know the first right endpoint, you just need to add change in x a bunch of times. Okay. So plus 1 over 25 times f of, what's the next right endpoint? Well, do negative 24 plus 1 over 25. Plus, what's the next right endpoint? Well, the same, right? We do, the length is the same, f of negative 24 over 25 plus 1 over 25 plus 1 over 25. That's negative 24 over 25 plus 2 over 25. again, similar as before, we add it again. Now we have f of negative 24 over 25 plus 2 over 25 plus 1 over 25, right? That's the extra change in x, plus 1 over 25. So that becomes negative 24. I keep writing 4 every time I want to write 2. So negative 24 over 25 plus now 3 over 25. And then we keep doing this. Well, how many times? Again, as before, we want 50 terms. So this is term 1. This is term 2. So if we want to get all the way to the end, we're going to do 1 over 25 f of, well, how many 1 over 25s we added? Well, we need to add 1 over 25 49 times as before, right? Because for the first term, we don't add anything. And then we need to add 49 terms. In each of them, we're adding 1 over 25. So it becomes negative 24 over 25 plus 49 over 25. And if you see, this last one simplifies to 1, which would be the right endpoint as we want it. Right? Negative 24 plus 49 is 25. 25 divided by 25 is 1. Okay. So we do end at the right endpoint, which is what we want. Now, how do we write this as sigma sum notation? Similar as before. We're going to have the sigma, some starting index, and some ending index on the top. And some expression here that depends on k. As before, there's only one thing changing. What's the thing changing? Well, it's the 1 over 25 that we're adding. Okay. So we put in the things that are always the same. 1 over 25 times f of negative 24 divided by 25 plus. Now, as I said before, we want to relate the thing that's changing to our index. Okay. But here we can do the same thing we did before. We can just do k over 25, over 25. And you can see that this matches, right? Because if we calculate a few terms, what happens when k equals 0? We get 1 over 25 times f of negative 24 over 25 plus 0 divided by 25, that's 0. For the next term, we do k equals 1. So get 1 over 25 plus f of negative 24 over 25 plus k equals 1 divided by 25. And that matches the second term. When we do this all the way till k equals 49. So let me write that here as a top index. So you always want to have a starting index and an ending index. So for the ending index, we go all the way to k equals 49, which is 49, right? So 49 over 25. There you go. And you see that it is the same sum. It's exactly the same sum. But instead of writing it this long way, here, we simplify it to one simple expression using sigma sum notation. And that's the idea. Now, this isn't exactly easy because it's new. Right? So I understand it's new. So let me just note this tip. What was the tip that I gave you? So when writing this expression, you're going to have a starting and not k equals 0 necessarily. You're going to have a starting index and an ending index. Here you're going to have some expression involving k. So since k is the thing that's changing, relate k to whatever is changing in your sum. And to show you, again, when we were doing these sums, we saw that the only thing was changing was when we added the 1 over 25. So it makes sense that in our sigma sum notation, we make our index represent that thing that's changing, which was the numerator of the fraction with 25. And that's how I got that thing there. And again, this is going to involve a lot of practice. So don't worry if you don't get it. This definitely takes a couple examples to do it. So you'll get enough of that in the homework, right? In my math lab, you'll be able to do this a bunch of times. And you should get it by then. So I know it's a little bit complicated. It's new. Hopefully you get it after you do a couple of practice problems. If you have any questions, please don't hesitate in telling me.